Here are a few problems that look at just sketching a graph of a polynomial only using the formula, not really a calculator. We're going to use the properties that the factors have along with the expansion with the leading term to what shape it should have, finding some x and y intercepts. So for this first one, we have a function negative 5 times the quantity x squared minus 4 times the quantity 25 minus x squared. So it would be extremely helpful if we could go ahead and get it factored all the way into linear factors so that we can see what the exact zeros will be. So we have negative 5, just a negative 5. X squared minus 4 is the difference of squares. It'll factor into x plus 2, x minus 2. 25 minus x squared is another difference of squares. It'll factor into 5 minus x and 5 plus x. So you can see that there are 4 linear factors. So this is a 4th degree polynomial. So depending on its leading term coefficient, it will either both point up at the end or they'll both point down at the end for long-term behavior. But for short-term behavior, we'll look at what the zeros do. This negative 5 out front, you know, you could do this x to the x and the x, and they'll be, see if you want to identify those. There's a positive x, a negative x, and a positive x. And if you combine all of those places, you will end up with x being negative. And you can even see that up here. See, negative, positive, oh, it'll be positive. Even in the beginning, the negative 5 to the x squared, and then that'll eventually get multiplied to a negative x squared. So in this case, our 4th degree polynomial is going to have a positive leading term, so the graph should point up at both ends for its general shape. So then if we go and look at the actual graph of it, your x-axis, here's your y-axis. You can plot the zeros, right? So your zeros are coming from setting your linear factors equal to 0. So we've got a negative 2, remember change the sign, positive 2, positive 5, negative 5. So 1, 2, 3, 4, 5, 1, 2, this is not drawn to scale. So here's the one at 2, here's the one at 5, here's the one at negative 2, here's the one at negative 5. So those are the x-intercepts. In order to get the y-intercept, remember that's where the x value is 0, in this case f of 0. So we'll take 0 and plug it in for all the x's in the function. So negative 5 times 0 squared minus 4 times 25 minus 0 squared, you get negative 5 times negative 4 times 25, ends up being a positive 500. So it's a really high y-intercept. So again, this is not drawn to scale, but up here is where I'm going to put the 500 for the y-intercept. So we have the zeros. It's a 4th degree polynomial. It only crosses the y-axis at one place, and we know that the ends have to both point up. So with those given 4 dots and my ends pointing up, it's going to come through the 0 at negative 5 and somewhere flips back up through negative 2, crosses through the y-intercept at 500, dips back down at 2, comes back up through 5, and the end behavior will shoot off to infinity at both ends. Again, the known factor of where the dips, you know, that minimum or the second minimum is something that will come later. But the sketch is, it has those zeros, it has that y-intercept, and the end behavior for the long-term behavior both point in the positive infinity direction. So again, it's just a sketch, but that's what the graph looks like. Here's another one. We have 5 times x minus 4 times x squared minus 25. That could be further factored to look at zeros. X squared minus 25 is the difference of squares, x plus 5, x minus 5. So we've got 3 linear factors, and if you were to take and multiply this out, you would get the leading term to be a positive x cubed as the leading term. So the shape for that is, something to this effect, where it rises on the right, falls on the left, may have a hump or two in the middle. It'll have at most two, and that'll be discussed in the next section. But as x rises, it goes to positive infinity, and the left half will go to negative infinity. We just have to figure out the intercepts, graph it, get the shape. So we do have zeros at positive 4, positive 5, and negative 5. So if I look at that on a graph, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So here's one at negative 5, here's one at positive 4, positive 5, they're pretty close together. So again, the shape will have to do something like this, but getting the y-intercept will be able to tell me exactly where it crosses the y-axis. So that's what I want to make sure that I get correct in a point. So in order to do that, we'll do y-intercept, which is where the x value is 0. So we'll go to the function. We'll do 5 times 0 minus 4, 0 squared minus 25. I think we have another 500 for a y-intercept in this problem, so I'll put it up here, completely not drawn to scale. So our function, again, it's cubic. It's going to have that general shape, so it does come up, cross the 500, dip down through 4, and back up through 5, and then shoot up to infinity. Again, it's a very loose drawing for the sketch, but it does dip down through 4. I don't know how far it comes down, but then it dips back up and hits 5 and shoots back up to infinity. So you can graph the zeros, the x-intercepts, and then you can find the y-intercept, and that will help you plot the graph more accurately without a calculator. One final one, just a little different because it does have a quantity squared. So we have this 0.5 out front, so that's a positive. And if we drag it through, I've got an x squared, another x, and another x. So if you count all of those, this is actually going to be a 4th degree polynomial. None of the x's are negated anywhere through the expansion, and the 0.5 out front is going to be the coefficient that you'll have. So it's a 4th degree polynomial with a positive coefficient. So the shape of that, the ends of it, will both point up on the end. And just we have to graph the zeros to see what it does in the middle for that short run behavior that's introduced in this section. So they're already in linear factors. So if you set that equal to 0, so x minus 2 squared, x plus 3, x plus 2, set that equal to 0. You've got a negative 3 here in the middle, negative 2 on the end. But what I wanted to be sure to point out here, let's see, is this x minus 2 quantity squared. The fact that that quantity is squared makes this what's called a double root, or a double solution. And the way that that affects the graph is, it's one of those where it's going to have an x-intercept at positive 2, but it's going to touch it, or just kiss the x-axis right at that, and then bounce back up, or bounce back down depending on where it hits with the pictures. Because it is a 4th degree, but one of those zeros are being counted twice. So let's see where that touches. So we've got, here's our x-axis, y-axis. We've got a 0 at negative 2. We've got a 0 at negative 3. And then at positive 2, that is where we need to indicate that it is a double root or double solution, and it needs to just bounce and touch that x-axis and come back most likely up. Finding the y-intercept here will help us get another point. So we'll set x equal to 0 in our function. You have a half times 0 minus 2 squared times 0 plus 3 times 0 plus 2. I think you end up getting 12 for this. So it's half times negative 4 squared times 3 times 2. Well, not negative 4 squared, negative 2 squared. So negative 2 squared, watch your signs, times 3 times 2. Yeah, you end up with 12. So 12 is the y-intercept, so up here at 12. And again, we know that it's meant to be an accent, not a negative. It's a 4th degree polynomial, the positive coefficient, so it's going to have this shape. So again, you can see the zeros in the y-intercept. So loosely, it's going to do something like this, make this little W shape. But more accurately, it needs to make sure when it comes off of this y-intercept, it comes down to 2 and just bounces and comes back up. And the other one dips down. Again, I'm not really quite sure where that minimum is here, but we can sketch it for now. But it still has that correct, it's 4th degree, both ends point up, in-term behavior or long-run behavior. Has an x-intercept at negative 3, then at negative 2, up at a y-intercept, and then bounces back at 2 to go back up to infinity. So again, it's just a sketch. You can't always check it on a calculator, but you should be able to use that information to come up with what the sketch of the graph looks like.